Good day everyone, especially to our instructor, Mr. Anthony Kamale. Good day to you, sir. Before anything else, let me introduce myself. I am Ipurgues Lombay Lustre, a second year criminology student at NOIS. Now let's proceed to my video presentation. In this video presentation, I will discuss the Chapter 2 Photographic Rays, its nature and characteristics. Light. Light in forensic photography is very important because we can produce picture if we don't have light. Light is one of a number of known form of radiant electromagnetic energy which travel in wave motion. When we say radiant energy, it is the energy that is transferred by electromagnetic radiation such as light, X-rays, gamma rays, and thermal radiation, which may be described in terms of either discrete packets of energy called photons or continuous electromagnetic waves. Actually, there are other theories that explains the behavior of light. Example, quantum theory. According to Einstein's quantum theory of light, it is made up of tiny packets of energy called photons that exhibit wave-like properties. Albert Einstein also addressed the mechanism of electroemission from the metals struck by lightning in this theory. This was known as the photoelectric effect, and it was this idea that led to the development of the modern television, giving technologists a fresh perspective on how to create gadgets with displays. But for our purpose, the wave theory is the only one considered. What is wave theory? The wave theory of light was the way we first understood light. The theory was spread most significantly by Robert Hooke and Christian Huygens in the 17th century. They predict that if light was a wave, we would see certain things. We would see that light could reflect off shiny surfaces, refract or bend when moving from one material into another, and diffract or spread around objects or when moving through slits. This form of energy travels at a speed about 186,000 miles per second in air, but they differ in wavelength and frequency. Wavelength. The wavelength is the distance from the crest, the highest point, to the wave to the next succeeding crest, while frequency is the number of waves passing in given point in 1 second. What you have seen is the crest of the waves. The crest of the wave is the point on the medium that exhibits the maximum amount of positive or upward displacement from the rest position. And this is the frequency of the waves. Wave frequency is the number of waves that pass a fixed point in a given amount of time. A higher frequency wave has more energy than a lower frequency wave with the same amplitude. So the product of the wavelength and the frequency is the speed of travel. Frequency is much more difficult to measure. Wavelength could be determined with accuracy. Hence, we identify a particular radiation by its wavelength. Wavelength is measured by the angstrom unit or in terms of millimicrons, English system of measures, or nanometer, a metric system of measure which is equivalent to 1/1 millionth of a millimeter. The speed of various radiant energy is constant at a given medium, but varies with other. For example, the speed of light in ordinary glass is only about 2/3 of its speed in air. Ordinary glass, for instance, has an index of about 1.5, so light moves through it at about 200,000 kilometers per second. On the other hand, light in air is 1.003 times slower than light in an ordinary glass. So the speed of the light in air is about 90 km per second. It's obvious that light can reflect. You just have to look in a mirror. Light bounces off the mirror and goes into your eyes so you can see yourself. It is also obvious that light can refract. All you have to do is put a spoon in a large glass of water and watch how spoon appears to bend. That happens because the light is bending as it moves between air and water. The different energies in the electromagnetic spectrum are the following: cosmic rays, gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, heat rays, Hertzian waves, and the alternating current oscillations. Cosmic rays. Cosmic rays are high-energy photons and atomic nuclei that move through space at nearly the speed of light. They originate from the Sun, from outside of the solar system, in our own galaxy, and from distant galaxies. Gamma rays. Gamma rays have the smallest wavelengths and the most energy of any wave in the electromagnetic spectrum. They are produced by the hottest and the most energetic object in the universe, such as neutron stars and pulsars, supernova explosions, and regions around black holes. X-ray. X-ray imaging creates pictures of the inside of your body. The images show the part of your body in different shades of black and white. Calcium in bones absorbs X-rays the most, so bones look white. Fat and other soft tissues absorb less and look gray. Ultraviolet rays. Ultraviolet or UV radiation is a form of non-ionizing radiation that is emitted by the sun and artificial sources, such as tanning beds. While it has some benefits for people, including the creation of vitamin D, it also can cause health risks. Our natural source of UV radiation is the sun. Infrared rays. Infrared, sometimes called infrared light, is electromagnetic radiation with wavelengths longer than those of visible light. It is therefore invisible to the human eye. IR is generally understood to encompass wavelengths from the nominal red edge of the visible spectrum around 700 nanometers to 1 millimeter. Hertzian wave. Hertzian wave is an electromagnetic wave produced by the oscillation of electricity in a conductor as a radio antenna and a length of ranging from a few millimeters to many kilometers. Visible light. Visible light is a light we can see, so is used in photography and illumination. It is also used in fiber optic communications, where coded pulses of light travel through glass fibers from a source to a receiver. The energies that are capable of being recorded on synthesized materials are the X-rays, ultraviolet rays, visible light, and infrared rays. So when we say synthesized materials, this refers to the chemical and physical means by which atoms and molecules are combined to form new materials. It is the major source for the discovery of new chemical and physical phenomena in solids. The X-rays, ultraviolet rays, visible light, and infrared rays are sometimes referred to as the four photographic rays of modern photography. The wavelength of X-rays is from 1 to 30 nanometers, ultraviolet rays from 30 to 400 nanometers, visible light from 400 to 700 nanometers, and infrared rays from 700 to 1000 plus nanometers. Actually, the wavelength of infrared rays extends beyond 2000 nanometers, but the longest wavelength that the present synthesized materials could record is only up to this limit. The Webster Dictionary defines light as a radiant electromagnetic energy that can be seen by the naked eye. So, according to the dictionary, light is a form of energy which a human eye makes the things visible. Light is defined as a form of electromagnetic radiation emitted by hot objects like lasers, bulbs, and the sun. The scientific definition of light is the aspect of radiant energy of which a human observer is aware through the vision sensations which arise from the stimulation of the retina of the eye. The light rays with wavelength of 400 to 700 nanometer is referred to as visible light because it is only within this wavelength that the human eye is capable of perceiving. So it says that our eyes can only see the wavelength that is 400 to 700 nanometers only. So example of the visible lights are the sun, light bulbs, candles, fires are all things that people automatically think of when it comes to light. But visible light comes from many sources and in many colors. But those with shorter or longer wavelengths are commonly referred as invisible radiations. So if the wavelength is above or below 400 to 700 nanometer, those are the lights that our eyes cannot see or can no longer see. So example of this are the gamma rays, infrared rays, and radio waves because it really needs machine to see the lights. By the definition, all lights are visible. For this reason, the word visible is superfluous in that common expression visible light. What the eye cannot see are referred to as radiations. Light energy has several effects on an object. It is either reflected, absorbed, transmitted, or converted. The varying combinations of these reflectance and absorption are what gives us the wide variety of colors which we are able to perceive. At times, other lights are neither reflected or absorbed but is transmitted through the object. This transmitted light passing through the object and allows viewer on the other side of object to perceive these light waves. The final effect a radiant energy may have on an object is to be converted to another wavelength. This conversion is known as luminescence. So what is luminescence? Luminescence is a spontaneous emission of light by a substance not resulting from heat or cold light. It is thus a form of cold body radiation. It can be caused by chemical reactions, electrical energy, subatomic motions, or stress on a crystal. There are two types of luminescence, the fluorescence and phosphorescence. Fluorescence is the ability of an object to convert one wavelength to another as long as the active energy source is irradiating the object. So here are some images of fluorescence. Fluorescence, in most cases, the emitted light has a longer wavelength and therefore a lower photon energy than the absorbed radiation. In phosphorescence, the object not only converts the wavelength while being irradiated but continues to reflect the new wavelengths of a period of time after the energy source is removed. When exposed to light of a shorter wavelength, a phosphorescent substance will glow, absorbing the light and re-emitting it at a longer wavelength. Unlike fluorescence, a phosphorescent materials does not immediately re-emit the radiation it absorbs. So it means the radiation that fluorescence absorbs will stay longer. So basically, fluorescence needs probably in electric energy to light itself. But the phosphorescence doesn't constant source of energy because it has an ability to absorb the energy. It enables it to glow itself alone. So here are some examples of phosphorescence. Now let's move to the next topic, white light. When all the wavelengths between 400 to 700 nanometers are presented to the eye in nearly equal quantity, we get the sensation of perceptions of colorless or white light. If a narrow beam of white light is allowed to pass through the prism, it will bend the light of shorter wavelength more than those with longer wavelength, thus spreading them out into the visible spectrum. These are the colors of the rainbows: the red, orange, yellow, green, blue, indigo, and violet. White light is defined as the complete mixture of all of the wavelengths of the visible spectrum. This means that if I have beams of light of all the colors of the rainbow and focus all of the colors onto a single spot, the combination of all of the colors will result in a beam of white light. If we divide the wavelength of visible light 400 to 700 nano equally into 3, from 400 to 500 nano, from 500 to 600 nano, and from 600 to 700 nano, we will produce blue, green, and red colors. These are known as the three primary colors of light, as differentiated from the three primary colors of paints, dyes, and coloring matters, which are the blue, yellow, and red. This table shows you the wavelength of the color, its frequency, and number of photons energy. So we are all wondering, why do we have to learn electromagnetic spectrum? It is important because by this observation, it enables us astronomers, not just astronomers but as the future investigators, especially photography, to determine certain physical characteristics of objects such as their temperature, composition, and velocity. The electromagnetic spectrum consists of much more than visible light. It includes wavelengths of energy that human eyes cannot perceive. Now let's proceed to additive color mixture. If we get three projectors, which beams of light projecting individually blue, green, and red, and have the three beams overlap over the other, we will note that the portion where the blue and the green light merged over the other, it will produce a cyan color. The green and red light a yellow color, and the red light and blue light a magenta color. At the center where the blue, green, and red light were combined in proper ratio, we will see white light. In these aspects, cyan, yellow, and magenta are known as the three secondary colors of light. For practical purpose, white is the presence of all colors, while black is the absence of all colors or the absence of light. So this table that I show you is the additive color mixture. Next is subtractive color mixture. This time, the light beams of the three projectors will be covered each with cyan filter, yellow filter, and magenta filter and have the beams of light projected one over to other. The cyan filter will transmit blue and green light but absorbs red from white light. A yellow filter will transmit green and red light but absorbs blue from white light. Similarly, a magenta filter will transmit red and blue light but absorbs green from white light. At the center where the three beams of light are merged, center will produce black. In simple terms, cyan is the complementary of red, yellow is the complementary of blue, and magenta is the complementary of green. In this table, we see that it is different now because the secondary color is mixed to produce a primary color. The cyan plus yellow is equal to green. The magenta and yellow is equal to red. And the magenta plus plus cyan is equal to blue. The primary yellow subtracts short wavelengths is equal to blue, and the primary magenta subtracts middle wavelength equal to green. The primary cyan subtracts long wavelengths, which is red. The range of colors which can be produced by subtractive mixture of three dyes is quite large and makes it possible the modern processes of color photography which depends on the subtractive principle. Now let's proceed to production of colors. There are a number of different ways in which color is produced. One need to know the variable quantities of colors so it will be possible to evaluate color as quality. Number 1. Absorption. The color of most ordinary objects are due to the fact that they do not absorb the same amount of light at each wavelength. Absorption depends on the electromagnetic frequency of the light, an object's natures of atom. The absorption of light is therefore directly proportional to the frequency. If they are complementary, light is absorbed. In this picture, we see that the green light is the only colors that we see in the leaves because the red, orange, yellow, blue, violet are the complementary colors, so therefore they absorbs in the leaves. Number 2. Scattering. The color of the blue sky is due to the scattering of light by the atmosphere. Variation in the density of the atmosphere gases act in such a way that they scatter light of the shorter wavelength at the sky and end up of spectrum much more they scatter light of the longer wavelength of the red end of the spectrum. Thus, the sky is the bluest when it is clear and white when it is less clear. Scattering occurs when light or other energy waves pass through an imperfect medium, such as air filled with particles of some sort, and are deflected from a straight path. A great example is when the sun's rays pass through clouds. The light is deflected off of its straight path and scatters in many directions. Number 3. Interference. Color can also be produced by interference of light waves in thin film like a soap bubbles or a film of oil floating in water. The light reflected from the top surface of such a film undergoes a reversal or phase, but the light reflected from the bottom surface does not undergo this type of change. This phenomenon is also responsible for the color pattern known as Newton's ring, which sometimes cause trouble in color painting work. What you have seen in the picture is a bubble which reflects a spectrum of beautiful colors when illuminated by natural or artificial light sources. Number 4. Fluorescence. This happens when molecules of the fluorescent materials absorb energy at one wavelength and radiate it at another wavelength. Number 5. Dispersion. Color may arise from differences in the refractive or bending power of a transparent medium of light of different wavelength. The rainbow is a good example of this phenomenon. Dispersion of light is a splitting of white light when it passes through a glass prism into its constituent spectrum of colors. Example: violet, indigo, blue, green, yellow, orange, and red. Dispersion figuratively means distribution, and that's exactly what is happening in the picture. The next topic is attributes of color. According to the modern scientific definition of color, it is not legitimate to ascribe color to an object but only to the light reflected from it. Thus, any color perception has three characteristics, any one which can be varied independently of the other two. These are hue, saturation, and brightness. What is hue, or how can you identify hue? Hue is described with the words we normally think of when describing color: red, purple, blue, and etc. Value is lightness, describes overall intensity to how light or dark a color is. It is the only dimension of color that may exist by itself. Chroma or saturation may be defined as the strength or dominance of the hue. What is saturation? So saturation is a range from pure color 100% to gray 0%. Saturation is sometimes referred to as color intensity. A fully saturated color is one of pure color, while a fully desaturated color appears as gray. Saturated colors draw attention due to their brightness and intensity. Last is, what is brightness? Brightness refers to intensity distinguished by the amount of shading mixed with the hue. Any desired hue of light can be produced when various amounts of two of the primary colors of light, so the primary colors being red, green, and blue, are combined mechanically either by additional or by subtraction. Next is bending of light. When traveling in open space, light travels in straight line. However, when light comes in contact with an object, it may be bended in the following manner. Reflection of light. So reflection of light is when light bounces off an object. If the surface is smooth and shiny, like glass, water, or polished material, the light will reflect at the same angle as it hit the surface. Next is transmission of light. When light travels through a glass, the intensity of the glass is typically reduced. This absorption happens when the energy of the photons of light matches the energy needed to excite an electron within the glass or its higher energy state. The photon is absorbed by the glass. Refraction. Refraction is the change in direction of a wave passing from one medium to another or from gradual change in the medium. Refraction of light is the most commonly observed phenomenon, but other waves such as sound waves and water waves also experience refraction. Kinds of object as how they behave to light. Number 1. Transparent object. Allows sufficient visible light to pass through them that the object on the other side may be clearly seen. Number 2. Translucent objects. Allows light to pass, however, diffuse it sufficiently that object on the other side may not be clearly distinguished. In some cases, the objects on the other side may be recognizable but sharp detail and outline are obscured. Number 3. Opaque objects. So greatly diffuse the light that recognizing the object on the other side is very difficult, if not impossible. Here are their examples images. Now let's move on to our next topic, sources of light. The first source of light is natural light. Those coming from natural like the sun, moon, stars, other heavenly bodies, lightning, fire, and etc. While all of these sources could now be used for photographic use. For practical reasonings, the discussion will be limited to sunlight only. With sunlight, there are actually several sources. Primarily, those coming directly from the sun, secondarily, those being reflected by clouds or the sky. The intensity of sunlight falling on an object in open space varies depending on the weather condition, time of the day, or even time of the year. For a more accurate exposure, sitting at daylight, only one character is considered, the kind of shadow casted by an object in open spaces. Bright sunlight, a lighting condition where objects in open space cast a deep and uniform or distinct shadow. Hazy sunlight, object in open space cast a transparent shadow. Dull sunlight, object in open space cast no shadow. Cloudy bright, objects in open space cast no shadow, but objects at far distance are clearly visible. Cloudy dull, objects in open space cast no shadow, and visibility of distant objects are already limited. Next is artificial light source. Light sources of this category are man-made and is divided into the continuous radiation and the short duration. Continuous radiation are those that can give illumination continuously. The common light source of this kind are the fluorescent lamp, incandescent lamps, carbon arc lamp, photoflood lamp, gas lamp, and etc. Short duration or flash unit. A flash unit gives a brief flash of light produced by a burning metallic wire of flash bulb or an electrical discharge through a gas-filled tube or electronic flash. At this time, the flash bulb is no longer available in the market, but the electronic flash remains very popular. The electronic flash offers a great light output in a compact, lightweight, and economical form. It does not have the effect of heat and glare during setup that are common with continuous light sources because it is the battery powered, It is most convenient for field work where AC current is not available. Like any other artificial source, flash units allows the photographer to control the direction, quality, and intensity of light to achieve a desired result. Next is forensic light sources. The number one source is ultraviolet lamp. Ultraviolet lamp used in forensic work come in variety of shapes and sizes and power. Some units are portable battery operated and are easily carried and can meet the rugged and rigorous demand for field work. The ultraviolet radiation is broken down into the long wave UV, the medium wave UV, and the short wave UV. The long wave ultraviolet radiation is used in a wide variety of applications in medical and forensics. The medium wave UV is often used in chemical analysis and is curing and hardening of different items for industrial applications. The short wave UV is used for variety of purpose such as to sterilize air and place of work. It is an effective germicide destroying many biological contaminants. Wave UV lamps used for medical and forensics. And this is the medium wave UV lamp used in chemical analysis and in curing or hardening items. This is the short wave UV lamps used for variety purpose such as sterilizing air. These lamps is commonly used for the COVID-19 patient's room. Next is laser. Light amplification through simulated emission of radiation. Laser, a device that stimulates atoms or molecules to emit lights at particular wavelengths and implies that light, typically producing a very narrow beam of radiation. Although developed years earlier, it was in 1970s that it was discovered by illuminating certain items with laser. They would flourish or could be made to stand out in sharp contrast from their background. This was especially significant in locating dried biological stains such as semen, urine, and saliva, as well as stains that had been washed. The laser stimulation of these items provided a way for criminals to finally see, locate, and visually record evidence that they know that they had been missing. The only drawback of laser is their cost. They are quite expensive. Laser is also known as coherent light. Lasers are used in optical disc drives, laser printers, barcode scanners, DNA sequencing instruments, fiber optic, semiconductive chip manufacturing or photolithography, and free space optical communication, laser surgery and skin treatments, cutting and welding materials, military and law enforcement devices for marking targets and measuring range and speed, and in laser lighting displays for entertainment. Semiconductor lasers in the blue to near UV have also been used in place of light-emitting diodes or LEDs to excite fluorescence as a white light source. This permits a much smaller emitting area due to the much greater radiance of a laser and avoid a droop suffered by LEDs. Such devices are already used in some car headlamps. Alternative Light Source or ALS. The alternative light source was developed in mid-1980s as a far more expensive alternative to forensic laser. The ALS uses a variety of band pass filter to provide a high-intensity beam of non-coherent light. These multiple band pass filters allows the operator to match the laser frequency available at crime scene. Additional wavelengths were included to allow the ALS to operate the UV, near UV, and IR spectrum. ALS technology had advanced to a point whereby using the combination of filter and adjustable iris to control the width of the transmission band, various wavelengths from UV to IR may be digitally selected. This allows the operator to scan an almost endless variety of wavelength instead of being restricted to the specific band pass filter capabilities. Now let's dig deeper to understand the alternative light source and its purpose. So one of the important rules of a forensic clinician is to perform examinations of patients who are victims and suspects of crime. Alternate light source or ASL or ALS is a tool that can improve evidence collection and enhance visualization of injuries. The purpose of this study was to examine if commonly used topical products fluorescence are absorbed when examined with an ASL. Secondly, we aim to identify patient and exam variables that may impact findings. The alternate light source can even see biological and non-biological evidence, such as lubricants, creams, and oils used to facilitate sexual assault may be identified with alternate light. Source of trace evidence can collaborate or corroborate the patient's history, even when the perpetrator intentionally uses a condom to avoid transfer of biological evidence. Next is forensic light source or FLS. The FLS is a term being applied to a wide variety of relatively inexpensive light sources which use filtered with white light. A band of pass filters allows a fairly narrow band of light to pass through. The object is then radiated with what is normally about 400 to 500 nanometer light source. The strobe shift of a specifically developed luminescent fingerprint powder which also falls within the strobe shift of most biological powder. This will enable a criminalist to search latent fingerprints of rough surfaces. The white light source used with the FLS is a sample of a maglite type handheld flashlight or a spotlight with the filter in place. A forensic light source is made up of a powerful lamp containing the ultraviolet, visible and infrared components of light. It then filtered down the light into individual color bands or wavelength that enhance the visualization of evidence by light interaction techniques including fluorescence or evidence glows, absorption, evidence darkens, and oblique lightning, small particles evidence revealed. Latent fingerprint detection. The primary application of a forensic light source is for enhancing the detection of latent fingerprints. The use of fluorescent enhancement processes that complement a light source greatly increases the type of surfaces from which a latent fingerprint can be detected. Consider the difficulties of dusting and lifting a print of the following surfaces: thin plastic bags, rigid duct tape, thin aluminum foil, heavily grained wood, concrete wall, brick, printed glossy magazine paint, uh, printed glossy magazine pages, paper products, and etc. Using the traditional methods, fingerprint evidence on these and other types of surfaces may go undetected or even dismissed because they could not be detected with enough detail. Forensic light source techniques have been successfully utilized for revealing latent prints on these and many other types of texture surfaces. Backgrounds with which mask rich detail, fragile surfaces, and contaminated surfaces. Goodbye and God bless us all. So this is the end of my video presentation. I do hope that I help you understand the photographic rays, its nature and characteristics. Thank you so much for joining me, and